So hi, I'm Gabriel. I am a front-end engineer. I'm also from Sweden, where it's going to be a weird accent. I am previously a founding engineer of a YC startup called Dataland. We were basically building a developer-first Airtable. And just like Airtable, one of our most important features, front-end-wise, is of course the table. So as a front-end engineer, one of my most important decisions to make was what kind of table are we going to use? We're going to use someone else's table, some open source table, build our own table. So that's kind of what I'm going to talk about. So just before the Dataland pivoted, I had a chance to experiment with a bunch of tables. And those are kind of tables that I would like to walk through now. I decided to start out using Grid, which is a really great open source library, lots of features, very widely used. So if I open up a table here, I just loaded in 150,000 rows into the UI. So since Grid already takes care of table rendering, the next step to build a really fast table is to do filtering, sorting, and search really fast. So if you, for example, do some filtering here on the phone, for example. So pick some numbers. This is pretty fast for 150,000 rows. Same with you do some searching. So searching 150,000 rows. Also pretty fast. So to put that into perspective, for example, Airtable, we're going to search for A, and it's a third of the rows at 50 kbytes, I think. It's pretty damn fast. So what makes it is fast? Also, that the locate from the Dataland is code that is no more used. The filtering itself doesn't really have that magic inside. How well can people see it? Huh?
Brighter.
Yeah, that is unfortunately not an option. So for the filtering logic itself, I'm not really doing anything super special. I'm just trying to have as few operators as possible. I'm trying to allocate as few operators as possible. I'm trying to not use a bunch of is5 pipe chaining, .map.filter, and creating a bunch of arrays for arrays. One thing that is pretty cool here, though, is this part right here, which is how we chunk up the filtering. So as we all know, JavaScript is a single-threaded language. So if you want to do something that takes 5 seconds and you just do it, the user freezes for 5 seconds, right? So we want to chunk up this work. So here I have some chunks of work, and I want to look through them, and I have a few different options to do them. So this is the first one, right? Just doing the chunk synchronously, freeze the frame for the user. Another very commonly used is using the request animation for it, which is pretty good. You will be able to run small chunks over multiple frames. The user will not feel that it's some heavy task is running in the background, like filtering, for example. The problem is you're doing some work, and then you're idle for a bit, and then you do some work, and then you're idle for a bit, because you kind of don't know how much time you can spend at any animation. So Chrome is this very, very cool function, which works super similar to request animation frame, which the callback will be called when the main thread is idle. And just like request animation frame, it will call itself recursively. So basically, when the main thread is idle, it will call itself recursively all the time until all work is done, which is very efficient. But every time you need to spin up a new task, there's still some overhead because you're creating new tasks instead of just running everything synchronously. And here is where this option 4 comes into play, which is something very not commonly used from the library main thread scheduling, and this is super cool. So main thread scheduling exports 2 different functions: is time to GIL and GIL control. So is time to GIL will check in the main thread and see oh yeah, is something running here? If something is running, we'll await it, until nothing is running anymore, and then we'll call shun, and then we repeat. The cool thing to notice here is that each time to yield is sync, it's synchronous, which means that if the user is idle, we can actually synchronously run through every single chunk, which is extremely fast. So the best case scenario here is really good, and also shown by this very nice thing here that we have no overhead here. But with all of this promised, as you can see, that's not really what's happening on filtering here. What I just said means that everything just is instantaneous, and we should never ever see any drop of frames. But as you can see here, I can't really just type out a bunch and remove characters very fast. It's definitely dropping a few frames here. And turns out this is because grid has a 500 millisecond chunk of work that's run every time you set data, and I wondered why. So I started looking into the code and saw some not very efficient code. So I did what any other developer would do. Let's build a bare bone grid and see how far we can push the performance of a grid. And I have two constraints. Actually, there's three constraints, but I don't have time to go into the last one. So the two constraints is it should be fast as hell, way faster than grid. And the second constraint is that this should not happen. When you scroll fast, you don't see your rows loading in, which happens because of the virtualization. The same happens on Airtable, it's a bit hard to see because the sensitivity. So what I built then was this table right here. Looks like trash, but it works really fast actually. So if I were to scroll here now, you can see that it's well, it would be about 60 FPS if possible. And also drag this thing right here, super fast, doesn't drop a frame. It drops a few frames here, but not on my computer. And this is a million rows, right? So this is a bunch of rows. You really can never handle a bunch of rows. Airtable supports 200k rows over all bases, or in one basin, which is multiple tables. And a grid is not that cool at all, it has some actions, right? So you can add rows super fast. And then yesterday night they added some more things to make it then a bit cooler, so you can reverse the rows. So there's a million rows that just get reversed. You can sort on this column right here. So let me do that. That takes around a second. And the coolest thing about is filtering now. So as promised by what I said before, so I implemented filtering from the last table to this table right here. So just make sure it works. Let's got some ones here. Here we have everything with ones. Oh yeah, let's fix the scroll. Yes, obviously you should do the scroll here, but I just didn't have time to fix that. So that works. So let's see if we can design like this. So right now you just spam out stuff. I'm never bottlenecked by the filtering. We just read. So the user will never be bottlenecked by some heavy computation. And what I think is even cooler, this is what I thought was the most cool. So if I scroll like this now, and I press 1, and I press 1 again, and in the background you see all columns in, or all the values here are now to ones inside. We did 2 filterings on a 1 million row table while scrolling simultaneously. I think that's really cool to do JavaScript nowadays. So how did I do this? So basically the most expensive thing when it comes to a table like this is just the DOM operations. DOM operations in general is extremely expensive. So you want to add all the rows, you want to add all the cells, you need to insert all the content inside of the cells. So how would you do that in a very efficient way? So what I did for this table is 2 things that I think is pretty cool. One of them are cool, the other one is basic. So when a row goes out of view here, say it goes out of control, it will actually come in from the bottom. So I'm just reusing the DOM here and just replacing the contents. So I'm doing as few DOM operations as possible. And all of the rows here are moved by transform. So it's not even a DOM operation, you can just do translate it in the GPU, which is super efficient. Also, you will notice that I'm using not a native scroller, but a this drawer. So this is for two reasons. The first reason is that there's actually a height limit in Chrome of how high a div can be. So it maxes out at 15 million pixels, and this is way above 15 million pixels. So therefore, like you literally can't use a native scroller for a huge table like this. Second of all, like if you use a native scroller, scroll events are treated very differently from other events in JavaScript. So a normal event would like pass through the link engine and you know, do all its computations, and then you see everything in the scope at the same time. A scroll event will just pass directly through to the viz process, which is where like a completely separate process where the GPU runs. So when you scroll, actually like Chrome has no idea you scroll. The GPU knows to scroll first, and it just instantly move all the content upwards. If there is nothing to show here, then there is nothing to show until something shows up. Hopefully there is something to show, and generally like, web pages render more content than you can see, so it always looks like, or like you always see when you scroll. But an example when this doesn't happen is like Airtable, for example. If I scroll fast here, you can see that the scroll events goes through before. Yeah, because it's white up there, so you can see the scroll events goes through way before it catches up. So I thought it was pretty cool, and then I did something like this because I wanted to work on very slow laptops. So this is on a X6 CPU slowdown, so this is like a MacBook Air from like 2014, no, 2007, or X6 slowdown is each and it still like works very fine, but I'm kind of curious in how I do stuff, so I wanted to like push the limits and see how far you can actually take it. So what I was thinking was like, this is by the way one of the best presentations and videos in front end that I've ever seen, like from Pixel can highly recommend. They go through like how Chrome works internally. Super interesting. They end with this very cool review right here of how Chrome works. And so what I was saying before is that Blink here is extremely expensive in our term. And what is actually expensive here is the layout. So we take the code, we parse it into DOM tree, we like check all the styles and where they should apply. We created a layout object tree, which is basically like traverses through the entire DOM tree and calculates the heights and widths of everything. And turns out by calculating heights and widths, everything is like really expensive, especially when it comes to like fonts, like or text. Like, text is extremely expensive to calculate. But since we know, like we want rows and cells, we basically know exactly what on the screen, like why we even need all of this really good software, but like very general software that's meant to like, you know, be able to generalize over all the years that like JavaScript and HTML has existed. So Blink starts with Paint. Paint is actually not painting anything. This is what you see in the performance tab, by the way. It says Paint. It's not painting anything. It's constructing a list of drawing operations actually that it passes into Skia. Skia is what actually does the drawing. It takes a list of drawing operations and draws down the screen with open GL, and that's when it's it. So Skia turns out to be written in C++, and that means we can use it with Rust. And that means we can make it into WebAssembly. Very cool, right? So we can actually use Skia, which is literally only used inside Chrome and Flutter right now. So if you do like the, I'm not too sure what the option is called, but I won't use it. But you can run the stuff in Skia and Flutter if you want. So this is what this looks like. Super cool. The red things here is like the composite layers in the GPU. I just wanted to visualize it. So this is like super, super fast, and to prove how fast it is, oh my god. Yeah. Also, I have to white because my screen is destroyed. I have to draw from obviously otherwise. So now it's impressive. What did I put this? Oh, yeah, fantastic. Okay, then we'll have to refresh this. Okay, so now this is scrolling a full viewport every single frame at 60 FPS. And there's one thing I haven't told you, we're actually running this in 6x CPU slowdown right now. So that means you could use a laptop from like 2004 and it would run at 60 FPS. It's really cool to me. I'll show you some yeah, so that's the kind of the story of like what I've been experimenting with. So super eager to answer any questions, or if I said anything wrong, it was super. I want to learn more about this because I'm super curious, and if anyone else is very interested in front-end, please come up to me and speak. Also, I'm using a MacBook from 2019, a Mac M2 renders even faster, which is super cool. Maybe for another demo. Yes?
Yeah, how would someone basically configure and install the necessary Rust
For this thing?
plugins? Yes.
Yeah, that was a shit show. There's one example on the entire web of someone doing this, which is in Rust Skia, and some guy just put some example together in the repository. So what I would suggest, I think we should target with this, and we'll forget it. Yeah, was put to on an script end, which is so you can import like the C stuff, which I import here somewhere. Yeah, here. And then you can use Rust Skia, which has all the bindings. And if you look at Rust Skia under the examples folder, I think there's an example of this. But yeah, that was the only thing that I found on the entire web that actually wanted Skia and it was. Any other questions?
I find it super fascinating. I think your pitch was super clear, and love to see the code as well. But a bit of a mean question is maybe what real problems does it solve?
Yeah, that's a very good question. I was thinking about bringing that up in my talk. Really, you know, if I have time. So basically, the problems we saw at Pebblebed where we had a bunch of people, first of all, who use, for example, Airtable, and Airtable is actually amazing when you start out. You can do so many things. But at some point, you know, nothing is version controlled. You have all these like inline functions. You have like super low row limits. Like we can literally have like 200k rows for like multiple tables in total on like the most premium subscription, which is like kind of crazy to us. So we built, this is basically an Airtable, but everything is code controlled, like schemas, functions, everything. You can do like so much more like granular actions for everything that happens in this shit. And of course it's like live collaboration and everything. And what we noticed was that like so many business people love our front. They love our front. They were like, oh damn, this front is awesome. We can just have, like everything's there, it's super fast. And we have like huge data sets, and we want to load larger and larger data sets into your front end. So like how can you make a really fast front end to just show everything? Like going to like paging, for example, but like I would prefer like doing like something like this, and then setting address and this, and then searching something like this, and then just being able to go through everything rather than put a bunch of like filters and search and page through something. That's kind of the reason why we didn't go for paging.
All right. Thank you.
Any other questions?
Any other questions? We have our last and not least. Okay. Thank you so much for your